Let's try another related rates problem. So again, we're going to go back and we're going to use the same kind of a methodology. We're going to try and understand the problem. We're going to try and develop a mathematical model of the problem using pictures and diagrams, making sure we distinguish constant quantities from variables that change. We're going to write an equation that relates the variable whose rate of change you seek with the variable whose rate of change you know. We're going to differentiate the equation that we just wrote. Then we're going to put in numbers and we're going to have a solution. So let's try it. A police cruiser approaching a right-angled intersection from the north. So here is my right-angled intersection, and here's my police cruiser, and he's approaching the intersection from the north. Right? North is up, south is down. When the cruiser is 0.6 miles north, so I know that this distance right here is 0.6. Oh, there's a car involved here too. It's a chase, huh? Oh, the speeding car has turned the corner, is now moving east. Okay, so I got a speeding car that's going in that direction, and that car is 0.8 miles from the intersection. So the police determine with radar that the distance between them and the car, well, that means that's not going this way here. That's going, the distance between them and the car, that's the distance between them and the car. That is increasing at 20 mph, 20 miles per hour. The cruiser, that means the police car right here, here's a police car, is moving at 60 miles per hour at the instant of measurement. What is the speed of the car? I want to know how fast that car is going. So, first question I always ask, what am I seeking? Well, we need to give some letters here. So I'm seeing a nice looking triangle. How about you? Okay. So let's call this side A, and let's call this side B, and let's call this side C. So I seek, well, I want to know how fast the car is moving. I want to know how fast this car is moving here. So this distance B here is changing. So I'm looking for dB to dt. That is what I'm seeking. Well, what do I know? Well, I know a few things. Well, I know that the distance A right at this particular moment is equal to 0.6. Now that distance is changing. That distance is not static. As the car is moving down, that A is getting smaller and smaller. But I also know how quickly it's getting smaller and smaller. I know dt. I know dA to dt. And that's equal to 60 miles per hour. But notice, that distance is decreasing. So that is a negative 60 miles per hour. What else do I know? Well, I know dc to dt is equal to 20, because they told me. They said it right here, that this distance right here is changing at a rate of 20. What else do I know? Well, I know that B at this particular moment is equal to 0.8. I know that C is equal to 1.0, and I know that because I can see that this is a 3, 4, 5 right triangle. So I know that this is equal to 5. I'm sorry, to 1.0. I'm not sure that's going to be important, but I got it right here, so I wrote it down. Is there anything else that I know on this problem? I don't think so. But I think this is all I'm going to need, but we will see. So I'm kind of developed a mathematical model here, and I need to write an equation relating the variable whose rate of change I seek with the variable whose rate of change I know. So and that's not asking for the rate of change yet, it's asking for the variable. So I have a nice right triangle here. So I know that a squared plus b squared is equal to c squared. And this is a variable whose rate of change I know. That's right here. This is a variable whose rate of change I know. That's right there. This is the variable whose rate of change I seek. So I could move this around to have the b all by itself, but I think it's just as easy to do it as it is. Now that I have my equation, I'm going to take the derivative with respect to time of both sides. Well, I have a sum here. So I know that I can take the derivative of a squared, and I can add it to the derivative of b squared. So I'm going to have d to dt of a squared plus d to dt of b squared, and that's going to equal d to dt of c squared. Now I need to do those derivatives. Well, the derivative of a squared is 2a, but remember, a changes with respect to time. So it's a function. I have to multiply it by the inside. That's dA dt. Plus, I got to do the same thing with b. The derivative of this is 2b dB dt, because that's the inside function right here. And this is going to be 2c dc dt. I've taken the derivative with respect to time of both sides of this equation. Well, that's kind of cool, because now I think I can start plugging in some numbers. So I have 2, now a, we know, is 0.6, 0.6. And we know dA dt is negative 60. Plus 2, do we know what b is? Yeah, we know what b is. b is 0.8. But what we are seeking is dB dt. So I don't know that yet. But I know that it's equal to 2 times c. Well, I'm glad I figured out what c was. Times dc dt, which they said was 20. Right? dc dt, right there, equal to 20. Well, this is making me pretty happy because I have a whole bunch of numbers and only one thing I am looking for. This is the only thing I'm looking for. So now it's really just a matter of crunching some numbers. So let's start with this piece right here. So I have 2 times 0.6 times negative 60. So that gets me negative 72. Plus, well, 2 times 0.8 would be 1.6 dB dt. And this is going to equal 2 times 1 is 2 times 2. That's going to equal 40. So I think I'll add 72 to both sides. And I get 1.6 dB dt is equal to, that would be 112. And now I'm going to divide both sides by 1.6, divided by 1.6. So I get dB to dt is equal to 112 divided by 1.6, 70. 71. Well, I want to know how fast is the speed, what is the speed of the car? Well, the speed of the car is 70 miles per hour.